My name is Hejlsberg, technical fellow, blah, 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 designer of C#. And I'm here now to talk about C# 3.0. This is, in a sense, a continuation of the previous talk about the Link project. And in this talk, we're going to take a deeper look at the language extensions in C# 3.0 that sort of underlie all of this Link stuff that we're doing. Just to sort of recap again what the Link project is for those of you who weren't here previously. It's basically about adding language integrated query to .NET programming languages and APIs to make set, query, transform operations first-class notions in .NET in the same way as classes and objects are first-class notions. And so you know, we have a series of language extensions to C# or VB. We have a series of APIs that take advantage of these language extensions. And so what we're focusing on in this talk here is the box in the upper left-hand corner, the C# 3.0 language. In terms of the design goals for C#, I sort of try to recap on this slide here what our value system is and what it is that drives us when we design the language. And of course, the high order bit for 3.0 is language integrated query that you've seen a lot of noise about here. But there are sort of some values that underlie that vision of a single programming model for objects, relational, and XML. And I'm talking about now the values particularly in how we're going about doing this. First of all, we are very serious about building on the foundation that we've laid in C# 1.0 and C# 2.0 to enable us to do these things. In particular, you really should think of the Link project as a multi-stage rollout. C# 2.0 lays a lot of the foundation work for language integrated query. If it wasn't for generics and nullable types and iterators and a bunch of the stuff that we did in the CLR to speed up delegates and so forth, it would be much harder for us to execute on this vision. So in the CLR and in Whitby, we've done a lot of work that now allows us to neatly plop on top of that this whole concept of language integrated query, and that's where we're going then in the next wave of C# 3.0. We have as a goal for this technology to run on the Whitby CLR. We require no changes, and there are no, in C# 2.0, generics was a feature that affected both language and CLR. C# 3.0, none of the features I'm showing you here today require any changes in the CLR. And indeed, all of the language integrated query stuff is done on top of the Whitby bids. And that's why we can release, you know, at this PDC a technology preview that you just put on top of Whitby Beta 2. We're very serious about not tying our language extensions to specific APIs and technologies. And to me, this is actually, as a language designer, a very, very important value proposition. I tend to think that languages live longer than technologies. So the minute you tie your language to a particular technology, you'll ride it all the way down, effectively, you know, when it goes out of vogue and the next great thing comes around. So you have to be very, very careful about not, for example, saying that C# now has language integrated query that only works on Yukon, you know, or that is particularly tied to, you know, whatever XML API so happens to be there. And so as a language designer, I find it very, very important to isolate what it is expressively that's missing in the language and adding that, but adding it in a way such that anybody else gets to play too. And indeed, there's nothing about the standard query operators and D-Link and X-Link and the APIs that are part of the Link project that is magic or special or could only have been done by Microsoft. These APIs, the language extensions are completely separate from the APIs, and anybody can go build language integrated query enabled APIs or or languages, other languages that support language integrated query on our platform. And I think that is the only way that you can assure that the language will be long-lived, is by not tying it to particular and specific APIs. Because, like I said, if we get object relational mapping wrong, well, someone will get it right, and C# will still be there. Not that we're planning to get it wrong, mind you, but and of course, there's always the 100% backwards compatible. That is, as always, that was for C# 2.0 a goal. It is indeed for C# 3.0 also a goal, and it does mean that we have to sort of play some funny tricks here and there in order to not break existing apps and yet sneak in what appears to be keywords even when they aren't, and so forth. But you know, still, I always think it is super important that we don't break code when we do these things. That said, it may be that the technology preview in the corners, you know, may do overload resolution a little bit wrong or whatever, but think of it as a technology preview. It will satisfy this goal even if it doesn't currently. Okay, so that's just sort of in a brief slide, you know, where we're going. I'm going to sort of try and just recap a little bit about query and then get into the language extensions. But just for those of you who weren't here previously, language integrated query basically allows me to write queries like this, you know, where I have an array of customers, and now I can say from C in customers, where C.city equals London. Whoops. Select new C.company name, C.phone. And I'll run this, and here I have my object dumper, and it'll show me the result of my query and so forth. And that's sort of what we went through in the previous talk. Now, this query expression I'm writing here with the froms, the wheres, and the selects, as I explained in the previous talk, you should think of this as a pattern on top of making invocations of a where method and a select method. In the same way that when you write a for each statement, the compiler translates it into a call to get enumerator, a while loop that calls move next, and blah, 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 blah. In the same way, we translate queries into method invocations. And really, I can sort of try and do the edit manually here to show you what happens. First of all, we remember that you called the range variable C. And then we get rid of the from here. And then we can put, then we can put a dot here. And then we can change the where keyword into a call to a where method with a lambda expression that calls the parameter C, and that's what we got from the from clause. And then we can turn the select into a call to a select method, again calling the customer C, and we just keep, you know, the expressions that you write. And this is effectively the transformation that the compiler performs. And indeed, if I run it, you'll see that it does the same. It produces the same result. And let me try and switch to slides now and sort of pick it up in slides and then look a little bit at the mechanics of that. So we'll go back here. So I wrote a query that was sort of like the one on this here. Now here I'm saying state equals Washington, selecting out name and phone. And the first thing you saw was this notion of query expressions, the from, the where, the select, and we also have order by and group by in there. And the compiler effectively does a literal translation of that. It does the translation before it binds types or anything, and it literally just constructs, you know, calls to a method called where and select, and then at a later phase in compilation, we discover whether there actually is a method called where or select, and if there isn't, then we get an error. So the translation happens at a syntactic level, and we'll take a look at how that happens. Another feature then we see in this query, and I tried to on this slide summarize all of the language innovations in one slide. And so query expressions is one. The next one we see on the slide here is local variable type inference. And we'll get into the mechanics of how all of these work. I'm just going to try and summarize them here. We see, well, we can't really tell here whether where and select are methods of customer or extension methods that extend customers' type, but it is now possible to do that, to extend types that, or add methods to types that already exist, and we'll get into how that works. Yeah, I know it sounds like black magic. It isn't. We have a lambda expression in here, and that's how we express predicates and select expressions and so forth. We're using an object initializer to perform our projection, and we're using an anonymous type in order to just create a projection out of thin air without first having to declare a type. So all of these language innovations we're now going to try and take a look at in more detail. And the first one I want to talk about is lambda expressions. I think the best way to sort of get comfortable and familiar with what these things do is to look at some code that already exists well or is part of Whitby. So in Whitby, we're shipping a class called list of t. And if you've looked at the beta bits, I'm sure you will have used this class at some point. It's effectively a strongly typed collection of some type t. And in list of t, we have a method called findAll that takes a predicate of t, and predicate is a delegate with a type parameter t. It is a function that takes a t and returns a bool. And the findAll method in list of t effectively for eaches itself and creates a list containing all of those items for which the predicate function returns true. And it's a handy method to use. And with C# 2.0, it might look like this to use it. We can new ourselves a list of customer, and then we can call customers.findAll, and then we can pass it an anonymous method. Let's say we want to find all the customers for which the state is Washington, the state property is Washington. We could write it like this with C# 2.0. And this is great. I mean, certainly a big step forward from having to create manually a method and new of a delegate to a method and so forth. But still, it's not quite as gentle as one could hope. There are a couple of issues with this when it comes to making it sort of the backbone of a query language. First of all, anonymous methods force us to explicitly type the parameters. When I write an anonymous method, I must say delegate of customer C, where the system could actually have inferred this for me. It knows that I'm operating on a list of customers, so why am I having to say customer again and again and again? And this is actually one of the things that sort of separate declarative query languages from imperative languages like C, C++, and C# is how much explicit typing do we force the programmer to do? And so that's sort of one thing that is a bit of an issue with delegates. Another issue is that the code you write, with anonymous method, another issue is that the code that you write in an anonymous method ends up in a statement context. So you must write open curly return c.state equals Washington, semicolon, close curly, and it's sort of like you're writing statements within your expression. Because really all you care about here is the fact that you're calling findAll, and you just want to pass the little predicate to findAll. You don't want to write all this stuff around it. And that's effectively what lambdas allow you to do. With lambda methods, you can write it like this, or lambda expressions. Customers.findAll, calling the argument C, for which c.state equals Washington. And we will do implicit typing of C, the parameter. It really is the same as customer C, but it's just the compiler infers that the type is customer, and you don't have to manually specify it. And the second thing is that you're put in an expression context, so you don't have to write open curly return blah 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 and so forth. You just write the Boolean expression in terms of C, which is given to you by the lambda. So it is effectively sort of a very compact notation for passing code as parameters, which is super important. If you think about what is it mechanically that's different about a query language from regular APIs? Well, in regular APIs, we pass parameters. We evaluate all the parameters up front, push them on the stack, call the API does something with them, and then it returns. But in a query language, we're not really, when you write a where clause like state equals Washington, it's not like we up front evaluate whether the state is Washington and pass that to the query engine. No, we pass a little piece of code to the query engine. We pass the expression to the query engine, and then it evaluates the expression for each item. And lambda expressions are really sort of the mechanism that makes that work. They're the glue, that allows us to now create query languages out of APIs. They are expressively, effectively, what is missing from our language, in order for it to be rich enough that you can create queries as APIs. Okay, so let me just sort of geek out a little bit more about lambda expressions here, just so you get sort of an idea of how else they work. In the standard query operators, we define a family of delegates called func that represent functions with 0, 1, 2, 3, up to some number n or 8 or whatever arguments, and they're declared as generic types. And they're very handy because this allows you to just construct a type of a function out of thin air without having to first declare it. For example, here I'm saying function of customer comma bool, which means a function taking a customer, returning bool. I'm calling that variable test, and then I'm assigning to it a lambda expression that checks whether the customer's state property is California. And you see that, or is Washington. You see the notation is fairly terse here. Here's another example of a function that takes a double and returns a double. And I can just write it in line here as a function where I'm calling the parameter x, and I'm returning x times factor. And here you see that I capture a local variable factor, and that's effectively how you get to parameterize queries if you're thinking about lambdas in query languages and so forth. Lambda expressions can have multiple parameters. So here I have a function taking 2 ints and returning an int. And now I'm writing a little anonymous method where I'm calling the 2 arguments x and y, and then I'm returning x times y. When a lambda has more than 1 argument, we put them in parens before the arrow. But in cases where a lambda has 1 argument, we allow you to omit the parentheses around the arguments. Finally, here's sort of a little, and this is starting to get geeky, an example of a function that takes 2 ints and returns an int, a comparer. And in this case here, I've actually explicitly typed the arguments of the lambda expression. I'm permitted to write the types there, but I'm not required to. Now, the way compilation of lambda expressions works is that when I write this lambda expression here, say c arrow c.state equals Washington, it, in and of itself, has no type, but it is a thing that is convertible to a compatible delegate type. And the way the conversion works is that we take first the argument type of the delegate, in this case customer, and we make that the type of C. Then we try to compile what is over on this side here, and if that succeeds, i.e. if C actually has a state field, and if the result of this is implicitly convertible to the result of the delegate type, then we say the conversion succeeds. So that is effectively how, a lambda becomes strongly typed. It is given strong type by whatever delegate type you assign it to, or whatever delegate type you use when you pass it as a parameter. Yeah, I told you I was going to geek out. So all of this stuff you don't necessarily have to understand, or you certainly don't have to understand it right now when I'm saying it in this room. This takes a little bit of study, but it's important to understand that lambdas are sort of the underlying mechanism that gives us enough richness in the language that we can create query APIs, and that is super important. Okay, so I'm going to go sort of on a little scenario here of this query API thing. Let's just say that we wanted to create a query language as an API now that we have lambda expressions. How would we go about it? Well, let's say that we wanted to take list of t and query enable list of t, just for the sake of argument, right? Well, so we would go to list of t, and well, it already has a find all, but let's say we want to now call the method where, and we also want to have a select, and we could have an order by and a group by and so forth. And how would we write them? Well, we would create list of t having a method where that takes a function that maps a t to a bool, and then it returns a new list of t which contains all of those for which the predicate was true. And we could have a select which takes a function that maps from some type T to some type S and returns a list of S. And that's how you sort of do projection and so forth. And you can imagine order by, group by, and whatever, all built as methods. So effectively, because of the richness of lambda expressions and delegates and whatever, we can declare query operators are just as methods. And then we can write code like this, where we new up some customers, and then we say customers.where, calling it c.state equals Washington, select c.name. And basically here you see methods composed to form queries. And that's really sort of the underlying mechanism, again, that we use in LINQ, is that we just have all of these relational operators, if you will, that dot together to form a complete query language. The cool thing here is that we have a type inference in the compiler that can figure out here what the type of S is. So you note that even though select is a generic method, the compiler can figure out what S is simply by, well, c.name. If name is of type string, well, then what you're going to get back is a list of string, and you don't have to manually specify it. So again, key to the illusion of having a query language out of methods is rich type inference in the language. But there are some questions here, though, that sort of pop up if we were to do it this way. What about other types? Like, how do I get where and select to work on an array? I can't write methods on an array. Do I declare these operators in every collection out there? That seems infeasible. And what if I get it wrong and so forth? So there's still something missing here. And really, if you think about how we would go about creating a query API today in C# 1.0 or 2.0, well, effectively, we would probably pick an abstraction like an interface, like IEnumerable of T, and then we would write all these methods in terms of IEnumerable of T. So let's see where that takes us. So now we would declare methods called where and select and order by and group by and blah, blah, blah. And instead of making them instance methods, we now make them static methods. We put them in some class somewhere, and then we make the collection itself the first argument of the method, and we type that as IEnumerable of T, and then again we have the predicate or the selector, and the rest is sort of the same. Do you know what I mean? And we all do this, you know, whenever we want to create a utility method that takes an array or whatever, well, we put it in a static class and make the array the first argument and so forth, and this is the same, you know. Now, this works, you know, we can actually have query operators like static methods, but when we write queries, what? You know, I mean, you look at this and you go, this doesn't look like a query to me anymore. Sequence.select of sequence.where of customers, comma, state equals Washington, comma, c.name. You know, things come in the wrong order all of a sudden. You know, things don't compose anymore. Really what we want is we want effectively to be able to declare methods on IEnumerable of T. If we could do that, then we would get our nice syntax, and we would get the ability to apply this to a multitude of types, not just the one type that we're writing. And in order to enable that, we have this new concept called extension methods. And really, it is a very, very simple mechanism, and it sounds magic, but there's nothing magic about it. Witness the transformation from the previous slide here. All I did was I put this class sequence into some namespace, and then I added a this modifier on the first parameter of the methods. And what this means is that this is an extension method. And the way to think of it is this is a method that extends IEnumerable of T. When it is in scope, it is as if anything that implements IEnumerable of T now has a method called where. But it's purely compiler magic. It's purely namespace magic lookup. You know, it's not like we actually modified anything in the CLR. It's just it looks to the user as if that method is there. And of course, you know, IntelliSense will understand it. Well, in fact, let's see how it works. When we say using system.query, that brings extensions into scope. And the way that works is that today when we import a namespace, we import all of the types in the namespace and put them into scope. With C# 3.0, what we also do is we put all extension methods in that namespace into scope. And the way we find the extension methods is that we take all static classes in the namespace and take all of the methods that have a this modifier on the first argument and put them into scope. That's all it does. So now we get to write customers.where blah 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 dot select blah 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 because a where method and a select method is now in scope for I enumerable of t. Now, the way lookup works is that we will actually first go look up where on customer, and if it itself declares a where method, that's the method we get. Only in cases where there is no such method do we then attempt to look up the extension method. So they sort of have second priority from regular methods. Now, we will, of course, support IntelliSense on extension methods. So when you import extension methods in your program, you know, IntelliSense will show them when you say dot. So you will see that there's a where and a select and so forth. Now, the way then it works is that after we do the lookup of a method, you know, so say here, for example, we're calling object.foo of x comma y. Well, we go to class. The class of object, see, does it have a foo method? No. Does it base class have a foo method? Blah, blah, blah. And we try and find it. And if we don't find it, today we would give an error. What we now do in C# 3.0 is we do an additional step where we change the call around. We take the this and make it the first parameter of the method call. And then we try to look up again in all of the extension methods that are in scope. And if we find one there, that's the one we call. And overload resolution and all of the other things that are in the language work exactly the same way. It's just a very simple mapping that takes the object and makes it the first argument of the method. That's all there is to it. Now, the ramification of it are pretty profound, though, because you can effectively now write methods on anything. And this feature should be used sparingly, and it is a big hammer. Yes. And I've had many a sleepless night about whether is this too dangerous and whatever. But what it enables is tremendously useful. And you know, in particular, if you start thinking deeply about it, the thing you realize is that with the advent of generics, it used to be previously that the only constructed types you could have were arrays. But now, and that meant that it was really not such a hardship that you couldn't write method on arrays. But now, constructed types can be very complex, dictionary of order, comma, blah, blah, blah. And there are lots of scenarios where you want to write methods on a particular constructed type. And this is the capability for that. And I think it's tremendously important to have that capability. And you sort of see with all the stuff we're doing with LINQ that there's a lot of power in having that capability. Okay, so that was just sort of a little bit of intro to some of those features. Now let's try and go take more of a look at how Lambda expressions work in code. So I'm going to switch to my demo machine here. And let's try and play around with this code for a little bit. First, let me show you some of the power of Lambda expressions here. We're going to take this code that we already have on the screen, and then I'm going to modify it a little bit. In fact, I'm going to pull these Lambda expressions out and make them separate variables, just to sort of show you how it all hangs together. So I can take and declare myself a function from customer, comma, bool, test equals, and then I can actually just grab the code from down here, say copy, and paste that up here. And then I could create another function of customer, comma, object, selector, equals, and then let me grab this guy here, this Lambda expression. So the first thing I want to show here is effectively that Lambda expression truly are the ability to treat code as parameters. Now I've taken my Lambda expressions and I put them into local variables, and now I can pass the local variables here instead. And it means precisely the same. So let's try and run it. And you see that we get exactly the same result. So try do that in SQL. Do you know what I mean? You can't pull your wheres and selects out and store them as local variables. So code, truly, this gives you the capability of treating code as variables, as parameters. And to sort of drive that home a little bit more, let's try to just really do some wacky stuff here. Let's say var tests. Let's create a dictionary of tests that are keyed by string. So we're going to have the user type in the name of the test that he wants to run in his where clause, and then we're going to find it in a dictionary. And we're going to make it all strongly typed. So we're going to say var tests equals new dictionary that maps from string to a function taking customer returning bool. And then in here we're going to say tests.add, and let's say we're going to have a test called London, and that test is calling the customer c.city equals London. And you see how we can actually put code in a dictionary here. So now we have keyed by string, and we're storing code in our dictionary that we can then later fetch out. Test.add, let's have another one called USA that tests whether the customer's country is USA. And let's write another tests.add of many orders that tests whether c.orders.count is greater than or equal to 15. Okay, let's then modify our code down here a little bit. Let's have a while loop where we say while true, console.write of what test do you want to run? Whoops. And then say string s equals console readline. And now we're going to take our query here. Whoop. Just indent this and put close here. And then let's modify our where to say run test sub s, because we've stored it in a dictionary. So make the user type in the name of the test they want to run, and then go get it out of the dictionary and pass that as the argument to the where. Let's try and run it. And so first, let's try and run the London test. Well, actually, one thing we note here is, well, we can't see that it's London. Well, let's go back and change our selector here also to be not just company name, but also let's get city, comma, c.country, comma, let's see, count equals c.orders.count. Okay, so we can actually sort of visually verify. Okay, so test is London. Let's try and run it. And now you see, yep, we got all the ones in London. Let's try and run the USA test. Yep, we see we get all the ones that are in the United States. Let's try and run the many orders test. And yep, we can see, yeah, they all have more than 15 orders. So you see how it's sort of, this ability to treat code as variables in a strongly typed fashion sort of opens up a whole new world of possibilities that previously sort of have eluded strongly typed programming languages. Some scripting languages have done this. Functional programming languages, to which we owe a lot in these features, do some of this stuff, but then they come with all sorts of other baggage, you know, and so we're sort of creating what I think is a very happy medium here. Okay, so that's a little bit about lambdas. Let me now try and play a little bit with extension methods. In fact, let's try and take our query here again. Just whittle this down a little bit, like so. And then let's, for example, have a query for customers, calling them C, where c.orders.count greater than or equal to 15. And from that, select, say, C arrow C.country. So give me the countries of each of the customers that have more than 15 orders. Let's just try and run this and sort of look at the result here. And we see we get some countries. And we see that some of the countries are in there several times, like Germany, for example. So one of the operators we have is a distinct operator that we can just use. And let's try and use that. And now we only see one. Whoa, something fell down here. Let's say we wanted to create our own extension method here, our own query operator. Let's say, for example, we want an operator that can join together a bunch of objects and put commas in between them. Take their string and put commas between them. We sort of have a method called string.join already in the BCL, but it only works on an array, and we want to sort of work it on an IEnumerable. So let's try and start out by writing that. So we're going to create class myExtensions, and in here we're going to create public static, or actually that's not class myExtension, sorry, namespace myExtensions. Public static string join of t that takes this IEnumerable of t source, comma, string separator character or separator that we want to put in between them. And in this guy here, oh, I guess I didn't close my namespace, sorry. There we go. Oh, public static string, I guess I am doing. Oh, sorry, yes. I need a class. What am I doing here? Sorry, it's been a long day. Public class, static class extensions. There we go. Okay. Put this in there. Put this guy here. Okay, now we're ready to write the method. And in here, what we're going to do is we're going to say string builder SB equals new string builder. Go. And then we're going to say bool first equals true. And then we're going to write a for each. And now we're going to for each on our source. For each var t item in source. If not first, then add the separator to the string builder. And then sb.append of item.toString. And then say first is false. So basically just, and then finally return sb.toString here. So this is a little thing that can take now an IEnumerable of anything and then call toString on each item and put a separator between them and return the result as a string. So let's try and use that in our query here. Then we can simply say dot, join of comma. So put comma blank in between them all. And we'll try and run, and we'll get an error here because it says, and you'll note, collections generic IEnumerable of string does not contain a definition for join. Yes, because we have not yet imported the myExtensions namespace. But witness now what happens if I say using myExtensions, and I now try to run, then it works. And I have now extended IEnumerable of t with a new method. Thank you. Now I could, of course, use, other things in here, like put 3 dashes or whatever, and so forth. Let's try and write another one, actually. Let's say that we want a convenience method that can take an IEnumerable of something and turn it into a little XML element that contains nested XML elements for each item in the array. We could write that as public static x element to XML of t, again, that takes any old IEnumerable of t and a name, a tag name, an XML tag name that we're going to create. And in this guy here, we're going to return a new XML element with the name that we gave, and inside of it, we're going to put, well, we're going to write a query over the argument that we're passing in. So we're going to say from item in, whoops, I forgot to say source up here. From item in source, select new X element, calling each of them item, and put into it just item, which will just call the toString on this guy. That's what the X elements constructor will do. So effectively here I'm saying return from this an XML element with the tag name that I gave and put into it a sequence of XML elements, each with the tag name item containing the toString of the item that I passed in. Let's try and use this guy and take our little query here and say to XML of countries. There, and let's try and run that and see what happens. And now we have a little operator that can turn arrays into, or IEnumerables into XML. Thank you. So you see, there are a lot of fun stuff that you can do with these extension methods. But like I said, a word of warning: you can do a lot of not so smart things too. Like, oh, my favorite 10 methods on object. Let me go declare those, and it should be done sparingly. Okay, let's go back and look some more at some of the other language extensions. So object initializers is one of the language extensions that we have in place for inline initialization of objects. Let's say I have myself a class called point with two properties, x and y, for example, and I want to create instances of point. Well, today I'm going to have to new up points and then assign to its properties in order to get myself a new point. With object initializers, we allow that to now happen in an expression context. So you can new a point, and then you can follow it with an open curly and a series of field or property assignments. So it's a fairly simple extension, actually, but it makes it possible now in an expression context to new up objects and initialize their contents, which is tremendously valuable. And certainly you saw in case of projections in databases or whatever, this is one of the sort of key workhorses to make the select operator work. Now, what the compiler does when you write this is it simply turns it into a new point and then assigns to each of the properties of the newly constructed point. You'll note here that I just said new point and I didn't have any constructor arguments. I could have given constructor arguments here, and that would have called that particular constructor and then performed the property or field assignments. The only little thing is that if I want to call the parameterless constructor, then I can omit the paren, because we know that there's an initializer coming right after. So it's the same as saying new point paren, as you see on the line below. So that's sort of, in a nutshell, what field or what object initializers allow you to do. There's actually, though, a little twist on object initializers, because this is great for just newing up objects, but sometimes what you want to do is you want to initialize. When you new an object, the object itself news up other embedded objects or embedded collections. It's a very common pattern. For example, imagine that we have a class rectangle here. And rectangle, when you create a rectangle, it news up 2 points internally and exposes those as properties, P1 and P2. And you see here that it exposes them just as read-only properties, but then you can mutate those two instances that are stored in the rectangle. So you could, So the problem is, how do we get that initialized with an object initializer? And we support that too. And here's what that syntax looks like. You say new rectangle, open curly, and then you can say P1 equals open curly. So you're not actually here specifying any type. And what that means instead then is that we will turn this into a get of that property and then apply all of the assignments to sub-properties of that property. So this effectively is the same as saying r.p1.x equals 0, et cetera, et cetera. And this turns out to be very useful because of our object models and whatever in a lot of situations, already knew up these embedded objects. We also have collection initializers, which are sort of a natural extension of array initializers and object initializers. You can now write new list of int and then just give the elements of the list right there in situ. And effectively, we say, as long as the collection implements I collection of t for some t, then we will permit you to write a sequence of expressions of type t. And we turn it into calls to the add method after we new up the collection. And sort of combining these two is what I'm going to do here. Let's say, just to sort of show you how you can create whole object hierarchies now in a single statement, really. Let's say I have a class called contact that has some private data. It has a name and a list of phone numbers. And the list of phone numbers is an embedded object that I new up when I'm newing up the contact. And then I expose a name property that's read-write. And I expose the phone numbers just as a get property because it's always that same collection. Now, I can write a complete object initializer, a mixed connection object initializer here, where I say new list of contacts, and then into that put 2 new contacts and assign name equals Chris Smith, and then phone numbers equals open curly, and you see how I don't say new here because that has already been newed up by the contact itself. So these things compose nicely and allow you to sort of new up entire hierarchies of objects in an expression context, which is very useful because the body of the select statement of a query ends up being an expression, and so you got to have the ability to construct hierarchical data in an expression context. Okay, so now here's the mystical local variable type inference. Here are some local variable declarations that I wrote, and you know, int I, string s, and whatever. This is all fairly simple stuff. One thing that we sort of observe is that as we get into constructed types and generics, sometimes it's a little painful to have to say dictionary of income order orders equals new dictionary of income order order. It's like, oh, how many times do I have to tell you I want a dictionary of income order? And so local variable type inference allows me to not constantly state over and over the type that is obvious from context, or at least in many cases is obvious from context. These 2 blue boxes are precisely the same. You could take one or the other. When it's compiled, it means exactly the same. So the var keyword means take the type on the right-hand side and use that as the type of the variable. It specifically does not mean variant or object or forget about the type and go to late binding or something like that. Rather, it is just shorthand for knowledge that the compiler already has. Now let me talk then about anonymous types. I wanted to sort of first set the stage with var and then talk about anonymous types. And we're sort of going to pick up again on this theme of how do I create a query language out of an API, and now let's look at how would we do projection in that world. Let's say I have a customer class, like I did in my example, and let's say I wanted to project some fields out of a customer. Now, one way I might go about it is by creating a class called contact, and then given a customer, I could new up a contact, and then I could write an object initializer, and then sort of project over values from the customer into the contact. And that's what I'm effectively doing in this piece of code here. I new up a contact, and then I say name equals c.name and phone equals c.phone. Now, the tedious bit here, though, is the fact that if all I'm interested in is just to have a projection with a tuple of name equals value pairs, and then I'm going to operate on those and then forget all about it, then why am I having to declare a class first? This sort of gets to be bothersome. And so witness the transformation. With an anonymous type, I can erase. I can simply just not say a type name here. I just say new, name equals c.name, phone equals c.phone. And then I put it into some local variable, and I use type inference to figure out what the type is. And what happens when I do this is that the compiler generates a class, and then it infers from my object initializer what properties to put into the class. So here it infers, name must be of type string, because what I'm assigning to it is of type string, and phone also of type string. Therefore, I get a class with 2 public fields, properties, name and phone, generated by the compiler. The only thing that's special about this type is it has a name I can't say. Other than that, it's just like any old CLR type. It's just a class. Now, to make matters even more terse, we allow a projection style initializer where when you say new, if what you're doing is just projecting into a property that has the same name as what you're projecting, then you can omit the blah equals. So these two boxes here are precisely identical, and it's really the same as saying name equals c.name, phone equals c.phone. And it is permitted as long as the expression you write ends in a name. And then we project over not just the value, but also the name. And now you sort of see here the workhorse of select, effectively. This is sort of the object-oriented projection operator. You simply create anonymous types and project over whatever data you're interested in. Just to sort of hammer it home and see mechanically what is it that happens when I write a query and how do the types flow. So I can write var contacts equals blah, 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 and you've seen this query enough times now that I'm not going to explain it, but the compiler maps this into contacts equals customers.where.select, okay? So the new C of name, phone creates an anonymous class with some name we can't say. And then the type of that class flows through the select operator, gets inferred by the select operator, and the select operator returns an IEnumerable of that type. And we use var to create a variable of type enumerable of blah, the name we can't say. And now when we then write a for each loop where we say for each var c in context, well, the way for each works is that the range variables type is the element type of what we're for eaching. So the blah comes out of IEnumerable, and now I am still in a strongly typed fashion dealing with a C of the correct type. And I get IntelliSense statement completion, compile time type checking here. And I think this is a super important feature because a lot of this stuff would be a boatload easier to do if we just forgot about types and went to late binding and whatever. And that's what a lot of scripting languages do and whatever. And then all sorts of magic becomes possible. But boy, you throw the baby out with the bathwater because, hey, sorry, buddy, no IntelliSense, no compile time type checking. And so we sort of did the hard work of actually flowing the types through all of these constructs. And now we can do all of the compile time stuff and all of the tools that you've become accustomed to work with this stuff. And that, I think, is very important. Oh, thank you. Okay, so query expressions. Now let's sort of talk in a little bit more detail about exactly how these query expressions work. So first of all, they are effectively language-integrated syntax for queries. And the actual syntax is I've sort of tried to write it in shorthand here. A query expression always starts with the word from. It starts with a generator. Then you can follow by 0 or more froms or wheres. Each generator introduces effectively a variable that ranges over a collection. And as you introduce more generators, you effectively create a cross product of all of the generators. It's like nested for each loops. You can think of it that way in terms of how scoping works and so forth. And the wheres are filters that can be written in terms of the variables that we're ranging over. Then we can optionally have an order by, and then we end the query either with a select or a group by. And then optionally, we can continue into another query. And really what this is the same as the into operator is really just the same as saying, take the result of this query and now write another query where the range variable is called blah, and then the whole thing repeats again. And it allows you to sort of write, instead of having to nest queries, it allows you to just string them together and keep going. Which is very handy because if you want to do the order by before the select or whatever, you just go one more time, with a new range variable name. So queries translate into method invocations. Basically, there's a pattern of methods, and we call it the query pattern or the query method pattern of where, select many, order by, and group by. And basically, when I write a query expression, the compiler turns it into invocations of these methods. The thing that's different about this than other constructs that you might try and compare it to is that this transformation from query expression to method calls happens before we bound any types at all. So we simply just, it's almost like a macro. We just turn it into calls to where, select, order by, and then we try to compile that. And then if there are errors, well, then the compiler will be smart enough to actually sort of unravel what happened and tell you, the reason why. But mechanically, that's what happens. And this gives us sort of a new degree of freedom because collections can themselves define these where methods and select methods and whatever. They don't have to be ours. They could be written by anybody. And because we just turn it into method invocation syntax, they could be extension methods. They don't even have to come from the thing you're querying. They could have been brought into scope with a using clause that you wrote earlier. So now you sort of see how all the pieces start to fit together here. Mechanically, the way the mapping works is that when you write a query expression over customers, we sort of map the source of your query to the thing that we start with. And then, because there's a where in my query, we emit a call to a method called where. And then we construct the lambda expression that we pass to where by taking the range variable name and the predicate expression that you wrote, and we put an arrow in between them and make that the argument of the where. And the same really sort of happens with select. Because there was a select, well, we create a lambda out of that, and then we just let the compiler compile that and figure out what happens from there. So this gives us tremendous extensibility in terms of how queries get resolved. And you can actually use this query syntax for a lot of things. In fact, strangely, you don't even have to necessarily return something that has I enumerable of t. You can do queries on any old type you have. So it's really more like a macro pattern, although macros come with a lot of bad connotations. So I I hesitate to call them macros. Okay. The final thing I wanted to just talk about then is expression trees. I'm sure you're all wondering then, when I did the demo of D-Link, well, how the heck do we get from these lambdas to a SQL query? I mean, what do? Do you grok the IL and then turn it into SQL or what? In fact, let's look at the example here again. You saw that with D-Link, we can point at a database and generate a strongly typed representation of the database. That's what we did for our Northwind. And then we end up with a bunch of fields or properties that represent our customers table, our orders table, and so forth. And then we can new up a connection to the database and then write a query from C in db.customers, where c.state, blah, 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 blah. The compiler takes that and turns it into db.customers.where. So it effectively calls table of t's implementation of where. That's sort of at the bottom of it, what's going to happen when I write a query, right? But how do we get from this lambda that we're passing there? How can we remote this lambda over to the database and have it evaluated? Because really, that's kind of what we want to do, right? And well, I mean, I guess we could try and take the IL and give it to SQL Server, but that's probably a bad idea. Really, kind of what we want is the ability to pass an expression tree to the server. We want to pass a tree that represents the expression that you wrote there. And indeed, that's how D-Link works. Table of T declares a method called where, but that method doesn't just take a function from T to bool, it takes an expression tree of function from T to bool. So the method asks for an expression tree, a strongly typed expression tree, mind you. We've said what the signature of the expression tree is going to be. And this type that we're using here is a type that's part of link called system.expressions.expression of t. Now what then happens, and expression trees really sort of is the ability now to have code as data. So when I write a lambda expression like C arrow C.states equals Washington, I can assign it to a delegate. And what the compiler will do at that point is create a method, create a delegate to that method, and now I can call it, and it's just an anonymous method. But I can also take the very same lambda expression and assign it to a variable or parameter of type expression of some delegate type. And what we then do is we emit an expression tree instead of emitting a method and creating a delegate to the method. But it's all strongly typed still. So really, the compiler transforms this into a creation of an expression tree. And you can sort of now think of the lambda expression as literal syntax for an expression tree. And you can think of the type system as making the choice between whether we want to generate IL or generate expression trees. But from the user's point of view, the syntax is the same. You're just writing a lambda expression. Or you may not have even written the lambda expression. You wrote a query expression that we turned into a lambda that then became an expression tree, if you see sort of how it all changed together. So here, the equivalent here is that we knew up a parameter expression of type of customer, and we knew up an expression node for c.state equals Washington, and then we knew up blah, 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 blah. You know, there's some mechanics behind this. But the important thing is that we now actually, as part of LINQ, have what you can think of as an extension to reflection that allows you to represent expression trees in terms of CLR metadata. So we have an object model for expressions on top of CLR metadata, and then the compiler has the ability to generate expressions using that object model. But you can manually generate these things. You can new them up yourself. You could write your own little lightweight parser that generates expression trees and give that to D-Link, and it will then turn it into SQL. So you see there's like extensibility at all levels in this system. And furthermore, there's nothing about this that is peculiar to D-Link. Anyone could go in and write an expression tree to SQL converter and run it on top of their favorite database, or write an in-memory database with language integrated query. It's completely extensible. And this is sort of the thing I talked about earlier, is like making sure that we don't tie the language to a particular API or technology, but rather that we just put the right quarks in place so you can make the atoms and the molecules out of that, if you will. Okay, so all right, so that is sort of a whirlwind tour of C# 3.0. I want to end just with a quick demo of the LINQ technical preview itself, and just so you sort of have an idea of what you get when you install it on your machine, which I hope you try to do. So when you install LINQ, we put a little we bring up this little web page here that's part of the install, and in here we have links to a bunch of documents that come along with LINQ. There's an overview of the LINQ project. There's complete documentation for all of the standard query operators here that you saw me use. So let me just try and bring this guy up. And we can sort of look here. We have documentation for where, select many, blah, 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 and it's in mind-numbing detail here if you're interested in reading about the standard query operators. We actually also give you the source code for the standard query operators. So you can go in and see yourself, how is where, select, order by, group by, how the heck did all of these things get implemented, and learn from it and use that if you're going to write implementations yourself. We have an overview of D-Link, X-Link, language specification for C# 3.0, et cetera, et cetera. Now, we also installed some really cool little examples. So let me try and open up one of the sample projects that come along with LINQ. One of them is a little sample called Reflector that demonstrates X-Link. And it sort of does it in a roundabout way to sort of demonstrate as many features as possible. You can point Reflector at an assembly, and then we reflect out all the metadata and turn it into an XML document. And then we have a transformation of that XML document into HTML. And it's all written using X-Link and a language integrated query, and it gives you sort of a good idea of for example, how we take an assembly and turn it into XML. Well, you can see stuff in here where, we load up the assembly and then, for example, the emit assembly method here, we new up an XML element called assembly and then put an attribute called name and get assembly.manifest.name. And then from type in all types where they are visible, group them by namespace, blah, 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 blah. And you see a bunch of language integrated query here to operate on in-memory data. So it's sort of interesting reading. We can try and run it here, and basically what it does is here we reflected on system.xml.xlink.dll, and here you see we sort of produce a little just textual dump of all of the metadata of that assembly. And if you go look at thank you. View source, you can see in here that it's just a bunch of auto-generated HTML. So there's lots of interesting learning that can be had from that one. We also have, this is probably my favorite little demo in here, the sample queries demo. Let me try and run it because it sort of is easiest to see what it is by running it. It's a little query explorer that comes along with 101 linked queries in a tree that you can go in and look at. You can see the code, you can click run, and then it runs and shows you the output of the code. And it just goes into examples for every one of the operators in there applied against in-memory data or D-link queries. And here we show you how all of the various SQL operators get generated, from your language integrated query. We have 101 X-link queries that show you how to load documents, how to do transforms, et cetera, et cetera. And then as a bonus, we have taken all of the XQuery use cases from the W3C website. They effectively publish a bunch of use cases that XQuery implementations are supposed to implement, and we've translated them all into C# using language integrated query, just to show you that this stuff can do everything that XQuery can do. Here, for example, is a little example of how you write an XQuery that takes a document and extracts all books that were published by Addison Wesley in later than 1995 and then returns, something with a book with a year, blah, blah, blah. I'm not going to explain exactly how it works. But here's the same query written using C# with from B and bib.element to bib.element to book, blah, 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 blah. And we can run it. And for all of these, we end up getting precisely the same result. And really, the code is no larger. So this truly has tremendous expressive power. The funny little story about this demo cost me $364, by the way, because I promised the dev team that I would pay them $1 per query that they put into this thing, and they just... But it was money well spent. Okay, so that's just a little tour of what we're giving you with links. So sort of to wrap up, there are a bunch of new innovations in C# 3.0 that I urge you to go play with. Really, go install Link and feel for yourself how revolutionary this stuff is, and indeed think about how would you use this in your own applications, or how would you use this if you're building third-party languages or APIs, how can they get query enabled and so forth. And give us feedback, please. I mean, none of this is set in stone. I mean, we haven't even shipped Whitby yet, and we're already talking about the next one. So there's ample time for feedback, and we really value your feedback on this stuff. So that's it. And here again, more information, and I will take... Thank you. Thanks. Thank you. I'll take a few questions, and then please do come to the Ask the Expert sessions tomorrow, or come to our track lounge. We've got lots of the people that worked on this stuff there, so we're happy to answer all of your questions. I'll take questions for another 6-7 minutes or so. So let's go over here.
Hi there. How broad or how ambitious are you with expression tree generation with, say, method calls within the Lambda and whatnot?
Anything you can write in an expression works in an expression tree as well. So yes, method calls, the whole shebang. Basically, we say there are a few things that we don't permit. We don't permit expressions that mutate. So we don't permit plus plus and minus minus because they capture L values, and that's sort of not meaningful to do in an expression tree. But pretty much anything you can write in an expression can be put in an expression tree also. Let's go here.
My question is on the extension methods.
Yeah.
Can we think extension methods is another way of implementing multiple inheritance?
No. Extension methods are not another way of doing multiple inheritance. The thing that's different about, I would say about multiple inheritance and extension methods is that this is methods only. It's not state. You can't implement extension fields. You can only implement extension methods. We are thinking about extension properties, which actually has some good uses. It's not in the preview, and there are some issues as to what would the syntax be, because they're just some little puzzles that we need to work through in order for us to do that. But so no, it's not like multiple inheritance. Actually, there's so many questions, so I'm going to go over here.
Okay. I'm also a language designer. I'm a designer of the Boo programming language. I'm not sure if you're familiar with Boo.
Which one?
Boo.
Yeah, okay, yeah. Cool.
So I see many of the things here were also addressing Boo. And I was thinking if you have considered, instead of adding like specific keywords to the language to implement, you cited macros, right? Have you considered doing that kind of thing with macro expressions and allowing users to actually extend the expression?
We thought about it, but the problem is you end up sort of creating a meta language now for how you create all of these, and it's like, where do you cut it off? I personally feel that we're sort of trying to strike some middle. Fundamentally, the extensibility mechanism in the language is methods. And now we have this new kind of extension methods that give you another axis of flexibility. And I hesitate to create another kind of mechanism there. On the other hand, it is so compelling to do it for query syntax, but still, we effectively say your extensibility mechanism is methods, and for queries, we're just going to give you a fixed syntax so we can all reason about the same thing when we look at a query. Do you know what I mean? Because otherwise, it's like, it gets to be mayhem, is what I worry about otherwise. But it's an interesting question. Over here.
Yeah, I was wondering if there's a plan to fully support lambda expressions in code DOM, specifically, say, to enable or simplify, say, data binding glue code in ASP.NET.
Yeah, I can't talk specifically about what we're gonna do with the code DOM. It's a good question. I'm going to have to owe you an answer because I don't know to what level we're going to go there. Right now, the code DOM doesn't really cover stuff that happens at the expression level, and therefore it wouldn't really cover any of this because all it sees is sort of classes and methods, and it doesn't understand the bodies. So I'm going to have to owe you an answer. But I'll take the feedback though.
Do you allow accessing private and protected members in extensions?
Yes, if they're in scope. An extension method for all practical purposes is just like a regular static method. The only thing that's different about it is that you have this modifier that marks it and has special lookup rules, but the body of the method, it's no different than a static method.
So I can take somebody's class and create an extension for it and call private, say, functions?
No, not unless, think of it this way, if you could write a normal method, a static method that did it, then you can write an extension method that does it. But if these are private members and you're not within that same class, no, then you can't. So there's nothing changes there, really. All right.
Thank you.
Will there be any help for reflection with extension methods?
Well, you can look for effectively the way extension methods get compiled is that we take, when you put this modifier on it, we just emit an attribute that says, hey, this is an extension method. And so normal reflection will allow you to discover whether a method is an extension method simply by looking for that attribute. It may be that we will put in, you know, a little property on reflection metadata that says is extension or whatever, you know. But even if we don't, it's pretty easy to find out. You just look for that attribute. Let me see, timing-wise. Let's go over here. Let me do 3 more questions, and then we'll end.
I have 2 very quick questions. The first one is why you decided to use classes instead of structs for anonymous types, and the second one is just what order are extensions evaluated?
Okay. Well, why did we use classes instead of structs for anonymous types? I think sort of the key reason really is that structs are intended primarily in .NET for things that are immutable, and you know, these things are not sort of meant to be immutable. Also, structs, once you get beyond 4 fields or whatever, really, you actually start degrading performance by using structs, and classes are just sort of the natural thing to do here. Structs, in many ways, are just an optimization in the CLR for a particular kind of type or family of types, preferably immutable types. Once you get into mutable structs, there are all sorts of issues, you know, that they're better avoided at that point. And in general, you know, the performance gains of structs are not as great as a lot of people think. And so we're just gonna, you know, I mean, by doing class, we allow, you know, we allow it to work for all the scenarios. Otherwise, we'd sort of have to switch in the middle if there are too many fields, or I don't know, you know. So structs were pretty much off the table right up front. Also, structs, when you use structs with generics, it's actually fairly expensive because we create code instantiations for every shape of struct of everything that you call for that struct type. Whereas for classes, we just share the code, and that's a lot cheaper. Let me go here.
With the extension methods, don't you sort of reintroduce the multiple inheritance diamond problem? And how do you cope with that? If you
there could be issues with if you're importing extensions from here and extensions from there, and they end up declaring a method that has precisely the same signature. Yes, you would have a problem. But hey, extension methods are just static methods, so call them using regular static method syntax then. So you know, there's a nice, easy, you know, normal solution to that problem. Okay, last question. I'll take over here.
Have you implemented or considered implementing recursive lambda expressions?
In what way do you mean recursive lambda? Or
well, if you have a lambda syntax, is it possible to describe it in such a way that it refers to itself? So you have
you mean
full recursion?
Right. So it refers to. You mean it refers to its previous value before you assign a new value to it, or is that what you mean? Or
exactly. So
yeah.
Recursive functional definition.
Yes. No, we do not have that capability currently. But hey, I would much value suggestions, so please send us suggestions, and this is a good one.
It seems natural that you could maybe adopt this keyword to refer to the lambda expression itself within the lambda expression.
Perhaps. Yeah, I mean, I'll have to go think about it. Right now, what we do in anonymous methods and lambdas is that we capture the L value whenever you refer to locals. So therefore, if you mutate, you know, I mean, if you say f equals some lambda, and in the lambda you call f, well, you're going to get the new value of f, not the old value of f. Okay, so I'm going to have to end because I think there's another presentation coming after me. But please come see us in the track lounge. Come to meet the experts, and we'll geek out some more. Thank you. Thanks for coming.